Swayam Prabha. Digital India. Educated India.
Welcome to Lecture 7 of CAD NPTEL video series. Here we are going to be discussing certain techniques to design solids. This is the second of the lectures in solid modeling. We can use Euler operators to design solids. Given a polyhedron model, one may want to edit it by adding or deleting edges, vertices, faces and genus to create a new polyhedron. One can use Euler operators for this purpose. There are two groups of Euler operators, namely the make group and the kill group. Euler operators are written as M, X, Y, Z or K, X, Y, Z. M represents the make group and K represents the kill group. X, Y and Z can represent any of the features: vertex, edge, face, loop, shell or genus. For example, MEV implies make an edge and a vertex, or in other words, we add an edge and a vertex to a polyhedron model. KEV represents killing or deleting an edge and a vertex. Operators are designed to satisfy the Euler-Poincare formula, which is V minus E plus F minus, within parenthesis, L minus F minus 2 times S minus G equals 0. We have seen this relation in the previous lecture. V stands for vertices, E for edges, F for faces, L for loops, S for the number of shells and G for the number of handles in case we are dealing with solids which are homeomorphically the connected sum of tori. Euler operators ensure that the Euler-Poincare formula is always satisfied. That is, using a finite sequence of operators, any polyhedron can be constructed from any other polyhedron or from scratch. You might want to think about using Euler operators to construct a cube from a tetrahedron, or vice versa, that is, to construct a tetrahedron from a cube. You might as well want to think about constructing a tetrahedron from scratch. Here are some details about the make group operators. MEV stands for make an edge and a vertex. This operator introduces a vertex in an edge, and all the other features are not introduced. Correspondingly, there is no change in the Euler-Poincare formula. The second operator, make a face and an edge, MFE. This operator introduces a face and an edge. The number of edges get incremented by 1, the number of faces also get incremented by 1, and since loops are associated with faces, the number of loops get incremented. There is no increase in the shell value, nor there is an increase in the genus value. Once again, there is no change in the Euler-Poincare formula. MSFV, make a shell, a face and a vertex. The number of vertices increases by 1. There is no increase in the number of edges with this formula. The number of faces increases by 1. The number of loops get increased by 1, and the number of shells would increase by 1 with no change in the genus value. Again, no change in the formula. MSG, make a shell and a genus. No change in the number of vertices, in the number of edges, in faces and in loops, but the number of shells increase by 1, and so does the genus value. Again, there is no change in the formula. Finally, make an edge and kill a loop. The operator MEKL. There is an increase in the number of edges, no increase in the number of faces. The number of loops get decremented by 1, no increase in the number of shells nor the genus. Once again, there is no change in the Euler-Poincare formula. This operator has a specific purpose. Recall our discussion from the previous lecture on internal loops, and recall how we introduced auxiliary edges to merge the internal loops with the external one. This was the first auxiliary edge, and this was the second auxiliary edge. So remember what we are trying to do here. We are trying to construct an edge or make an edge, and in the process kill this internal loop. Once again, we are trying to make an edge or construct an edge, and in the process we are trying to kill this internal loop. The operator MEKL is specifically designed for auxiliary edges. Now, the kill group of Euler operators. The first is KEV, that is, kill an edge and a vertex. The number of vertices would decrease by 1, and the number of edges would decrease by 1. Correspondingly, there is no change in the formula. The second, kill a face and an edge, KFE. No change in the number of vertices. The number of edges decrease by 1. The number of faces decrease by 1, and so does the number of loops. No change in the number of shells nor the number of genus, and therefore there is no change in the Euler-Poincare formula. The third one, KSFV, kill a shell, a face and a vertex. The number of vertices decrease by 1, the number of faces decrease by 1, and so does the number of loops. The number of shells decrease by 1. No change in the Euler-Poincare formula. The fourth, kill a shell and a genus. The number of shells decrease by 1, and so does the number of genus or the number of handles. No change in the Euler-Poincare formula. Finally, we have KEML, which stands for kill an edge and make a loop. The number of edges go down by 1, the number of loops increase by 1, and there is no change in the Euler-Poincare formula. If you think about it, the make group and the kill group of Euler operators are designed such that the Euler-Poincare formula is always satisfied. What would that mean? Theoretically, this would mean that if one would start with a polyhedron and start constructing or start using these operators, namely the make group operators and the kill group operators, one would assume that all intermediate results would be valid solids. In general, this may not be true, but still one would have that impression that all results are valid solids. Eventually, when the final polyhedron is constructed, it would be ensured that it is a valid solid. Let's try now to construct a cube using Euler operators. The first step, make a shell, face and a vertex. These are the respective increments in the number of vertices, edges, faces, loops, shells and genus. What we have done is we have hypothetically constructed a shell. We still have to bind it with the enclosing faces, but for now let's assume that this is a hypothetical shell, and we have introduced a face at the bottom and a vertex right here. The next step, make an edge and a vertex. This would increase the number of edges and vertices. Correspondingly, the construction is shown here. This edge and this vertex get newly introduced. Try to appreciate the intermediate results. At this time, none of them would be valid solids, but still the Euler-Poincare formula will be satisfied. The third step, once again, make an edge and a vertex. The number of vertices and edges increase by 1 each. This is the new edge and a new vertex introduced. Next step, make an edge and a vertex again. The next step, make an edge and make a vertex. Once again, make an edge and make a vertex. Once again, now make a face and an edge. The number of edges increase by 1, the number of faces and the number of loops, they both increase by 1. We have introduced the top face and the rightmost edge on the top face. Make an edge and a vertex. Introducing a vertex and an edge at the rightmost corner of the cube. Make a face and an edge. A new face and a new edge gets introduced here. Make a face and an edge again. This is the back face right here that gets introduced. Make a face and an edge again. It is this face now that is getting introduced. Make a face and an edge. It is the face closest to you getting introduced. And finally, make an edge and a vertex. If you look at this polyhedral model closely, what remains is to construct this edge and this vertex. We have just about finished the construction of a cube using Euler operators. The next technique is called the constructive solid geometry, CSG for short. It is based on this basic premise. that solids can be generated by combining primitives using Boolean or set operations. We have seen those operations before. I refer to addition, subtraction, union, and intersection like set operations here. Primitives can be block, cone, cylinder, sphere, a triangular prism, a wedge, a torus, and many others. Primitives can also be user-defined solids that one can design and store in a library of a solid modeler. These are some examples of basic or analytical primitives. We see a cone, a block, a sphere, a wedge, a cylinder, and there could be others. Let's talk about constructive solid geometry operations. Step 1. Primitives are first instantiated, which means copied, and then transformed, and then combined to form more complex solids. Instantiation involves making available a copy of the primitive from the database. I'll explain this step to you later. Transformation is required to scale or position a primitive with respect to a few others which are there available in front of your screen. The primitive may then be joined with, cut from, or intersected with an existing solid to get the desired features. These are the set operations. Let's see the example of how to construct a bracket using constructive solid geometry. If you think about it, an L bracket can be thought of a union of two blocks, appropriately positioned with respect to each other. Let's take the block as a primitive. Let's assume that this primitive is available with the database. I first copy it onto the workspace, which is the process of instantiation. I perform scaling to get block 1, and then I perform transformation to appropriately place it in the workspace. I make another copy of the block available to me in the workspace. In other words, I instantiate this block again. I scale it appropriately to the dimensions of block 2, which is seen in the top figure. I transform it to place it properly with respect to block 1, and then I perform Boolean join, which is a union of two blocks to get the L bracket. How would this operation be seen by a solid modeler? Or how would this operation be simulated by a solid modeler? Let's try to understand that. The block primitives above may be treated as objects named block 1 and block 2. They may be identified respectively by 3 dimensions: the length, the width, and the height of the blocks. The copies of the initially standard sizes can be at the global origin. One may scale the 3 dimensions of a block by factors x, y, and z using, say, the scale command. Look at the representation in the red, which says scale block 1 by factors x1, y1 and z1. This is the scaling operation. One may translate the block so that the reference point would be shifted by, say, coordinates a, b and c with respect to the global origin. This command is represented by translate scale block 1 with factors x, y, z and translate by coordinates a1, b1 and c1. Similar operations for block 2 will be to translate within parenthesis scale block 2 by factors x2, y2 and z2 and translate by coordinates a2, b2 and c2. The two blocks would be united using the Boolean union or join command. This is how the entire operation would look like in text. We can represent the same operation graphically using the history tree. Like I said, CSG operations can be represented as a tree graphically. Let's take a look at a slightly different example. This is an L bracket with 2 through holes. We'll start with block 1. We'll transform it. We'll take cylinder 1. We'll transform it. And we'll perform a subtraction operation. So if you imagine that this is block 1 and this is cylinder 1, what we have done here is we have first made a copy available of block 1 in the workspace, transformed it appropriately, and then we have introduced a copy of cylinder 1 in the workspace, transformed it appropriately, and then we have subtracted the cylindrical feature from this block. We can do something very similar for the second block and second cylinder. That is, we take block 2, transform it, we take cylinder 2, transform it, and cut the cylinder from the block. Doing so would give me a block with a cylindrical hole here. And then I can perform Boolean join operation to join this block with this block. We have seen two kinds of Boolean operations already, namely the subtraction and the Boolean join. Let's talk about some more operations in detail. Two sets or solids A and B. If we have two solids A and B, their union, which is represented by A union B, consists of all points belonging to the two solids. Their intersection, represented by A intersection B, would consist of points which are common to both A and B. The difference, A minus B, would consist of points in A but not in B. Similarly, the difference B minus A would consist of points only in B and not in A. Try to appreciate the difference between the intersection operation and the subtraction operation. I emphasize again that intersection operation would give us points which are common to both solids participating in Boolean operations. Whereas in the subtraction operation, for example, A minus B, it will give us solid with points only in the primitive A but not in the primitive B. Let's take a few examples on Boolean operations. Very simple ones. Let's say a sphere and a cube are interacting with each other via different operations, via different set operations or Boolean operations. Imagine that I have transformed the sphere to lie over the top face of the cube in such a way that the center of the sphere rests on the top face of the cube. The union of the two primitives will look like this. The intersection would look something like this. I have rotated the view here to show the result better. The result, cube minus sphere, will look something like this, and the other way around, that is, sphere minus cube, will look something like this. So this very simple example that simulates interaction between two very basic primitives, the sphere and the cube, can result in different solids if different set operations are performed with them. Let's now talk about regularized Boolean operations. I'll tell you a little later why the Boolean operations cannot be applied in the raw form the way we discussed in the previous slide. Recall that the interior IV of a solid includes all points within the solid and not those on its boundary. A point Q is exterior to the solid if there exists an open ball of radius r centered at Q such that the ball does not intersect with the solid. A set of all exterior points is termed as the exterior of the solid, represented as E of V, where V would be a set of all points belonging to the solid. These are definitions that we have seen in one of the previous lectures. Points that neither belong to the interior or exterior constitute the boundary BV of the solid. The closure of a solid CV is defined as the union of its interior and the boundary. That is, CV equals IV union BV or IV plus BV. Note that in general, union and addition operations might give us different results, but in our case, the sets IV and BV are disjoint. They would not have any element common between them, for which reason the union of the interior of the solid and the boundary of the solid, or the addition of the interior and the boundary of the solid, would give the same result. Alternatively, the closure of a solid is the complement / EV of its exterior. Here is where I will explain why raw Boolean operations may not be used. There are certain drawbacks of the Boolean operations. Let's take this example. We have a cube and we have a cylinder. We have positioned the cylinder in such a way that one of its faces rests on one of the faces of the cube. Say the cube is solid A and the cylinder is solid B. If we perform the intersection operation between the two, we'll be left with a disk, and this is a lower dimensional result. It's a two-dimensional result and it does not represent a valid solid. This disk has no thickness. So a raw intersection operation, for example, in this case, can lead to lower dimensional results. That is why we need to regularize Boolean operations. This is how we do it. To eliminate lower dimensional solids, which are not solids at all, we compute the result as usual. That is, we compute the result as if we are performing a raw Boolean operation. And then we compute the interior of that result. We compute the closure of the result in step B. For example, a regularized union will look something like this. We have two solids A and B. We perform the union like a raw union. We compute the interior of this result, and then we perform the closure operation, which would be the union of the interior of A union B and the boundary of A union B. Likewise, a regularized intersection operation will look something like this. We perform raw intersection between the two solids. We compute the interior of this result, and then we perform the closure operation. Here, we perform the union between the interior of A and B and the boundary of A intersection B. A regularized difference can be thought of in a similar manner. Compute the difference as usual in the raw form, A minus B. Compute the interior of A minus B, and then perform the closure operation. Using the cube and the cylinder example, let's try to understand now how would regularization help. Recall that we had computed the intersection between the cube A and the cylinder B to get a low dimensional result, which was a disk. Let's take into perspective regularized intersection. We compute the intersection of A and B in the raw form to get a disk, and if we now compute the interior of the disk, we'll find that the result will be a null set, and the closure of a null set would again be a null set. In a sense, therefore, while raw intersection gives me a low dimensional result, which is a disk, a regularized intersection of the cube and a cylinder posed relative to each other in this manner will give me a null set, which is what is expected. Let's now see an example with constructive solid geometry with reference to the history tree, which is shown in the figure here. We are trying to construct a bolt. Each of these nodes here represent the thread revolved by 360 degrees, and it has a pitch value P. These threads can be joined together. These joints are represented by these nodes here to give us more threads. Some more of these threads can be joined together to give the threaded structure, which is now hollow from within. This node here represents a cylindrical primitive, which is the shank of the bolt. This node here represents the hexagonal head of the bolt. They can be joined together to get this intermediate result, and these two results can be joined together to give me a hexagonal bolt. In a similar manner, one can think of constructing very complex solids with very complex features. For example, this RoboSlot, which was designed by a few of my BTech students in their final year project. The students analyzed this design in the soft form thoroughly before manufacturing it. After verifying the model of a RoboSlot in soft form, they prototyped it and tested it. This is how the robot works. The robot is designed to scale a thin rope. It has two grippers at the end. One of the grippers would release itself and move back and forth on the rope, while the other gripper would ensure that one end of the robot is stationary, just like a natural slot. This is where the robot is scaling a vertical rope. The point I emphasize here is that it's always better to evaluate any design in soft form and ensure almost 100% that the design is going to work before one can think of prototyping it. And this is where solid modeling comes in very handy. The robot is now trying to get down. There are other techniques that different solid modelers tend to use to generate primitives. They are essentially categorized or classified as sweep operations. One can come up with a cross section something like this, with outer and maybe a few inner loops, and one can think of extruding this entire cross section in the third dimension to get a primitive like this. This is called the linear sweep operation. Alternatively, one can sweep a cross section, in this case for example, two circles here, along a nonlinear path in the third dimension. This is how the solid looks like. This is called the nonlinear sweep operation. Both linear and nonlinear sweep are categorized into translational sweep operations. They are translational sweep solids. Likewise, one can think of rotational sweep as well. For example, one can come up with any cross section. In particular, this is a cross section obtained by a closed spline curve or a freeform curve, and one can revolve it about an axis, in this case vertical, to get this solid. This is the rotational sweep operation.